Hello everyone, welcome back to Calculus 1, and this time we're going to work on section 4.3, maximum and minimum, maximum values and minimum values. And first, I think I needed to clarify concept. Speaking of maximums and minimums, there are two kinds of maximums and minimums. The local maximums and minimums and absolute maximums and minimums. Look at the first graph. Basically, I'm using the graph just from the textbook. Okay, you look at this chart closely, and what I'm trying to say here is, well, actually, it is printed on the book, and this is the point. Looks like, well, it is at x equals 1. That's a lower point. But it is really not the smallest value for the entire function, right? Because on this side and the other side, it keeps going down. So in this case, we want to recognize at x is 1, at x equals 1, or around x equals 1. Okay, this is the lowest point. So it is called as a local minimum. There's a local minimum at x equals 1. And similar at this point, x equals 0, it is a highest point around 0. But if you look at the other side, there are all other points, there are all other values higher, bigger than the value at x equals 0. Okay, on this, especially on this side. And still, we want to recognize this is a point highest, okay, around this point 0. So we call this as the local maximum. At the same point, at the same time, you really look at this corner point here. It stands on the very top of the graph function, and it is also considered as a local maximum. Local maximum. So simply put, for this graph, the function has a local minimum at x equals 1, and there are two local maximums at x equals 0 and x equals 2. And one thing you may want to know, local minimum, it is really not necessarily the smallest value. And the local maximum, it is not necessarily the biggest value of the function. That's a local concept of local maximums and local minimums. And mostly in this part of discussion, we are going to focus on absolute maximums, absolute minimums, and we will explain that in a moment. But anyway, before we get to the absolute concept, let's talk a little bit about the Fermat's theorem, and it is about where we possibly can get a local maximum, local minimum. If the function has a local extreme, which includes both maximum and the minimum, and then if the function is differentiable, and then the derivative of the function at that point must, sorry, I have to correct this, it is 0. So simply put, okay, this simply it is saying when you have a local maximum, very likely, or minimum, the derivative at that point, there's a horizontal tangent line right here. At the maximum point, at the minimum point, there's a horizontal tangent line. The local maximum, the derivative, the local maximum and the local minimum very likely will occur at the point of derivative 0. And also, you look at the other case, if you remember, at this point, it's a corner point. It's not a smooth, really, which really means the function, it is not a differentiable. There's no derivative. Derivative does not exist at this point. Derivative does not exist at this point. Okay, so in general, well, you may expect a local maximum or minimum at a point where the derivative is 0 or derivative is not defined. So the point, the passable points where the function may have a maximum or local maximum or minimum, it is a critical point, or a critical point simply where it is a point where the derivative is 0 or derivative is not defined. A critical point, okay, a critical point. And actually, these graphs may show better idea where the possibly local maximum or local minimum may occur. And yeah, this is the situation. And also, we could have the situation when when the local derivative, it's only possible, okay, that when the derivative is 0, and you still may not have a local maximum or minimum, right? You look at this point, derivative is 0, and it's sitting somewhere in between. It's not a maximum or minimum at all. And also, look at this situation when the derivative is undefined, and still it's sitting somewhere in between. There's no maximum or minimum at all. Okay, and at the point, the local maximum or the minimum may possibly occur at a point where derivative is 0 or derivative not defined. And even derivative is 0 or derivative is not defined, still you may not have maximum or minimum at all. That's all I'm saying here. But anyway, usually to find out the maximums and minimums, we do start from the point where the derivative is 0. Absolute maximum, and the absolute minimum. Let's just take a quick look about those charts. Look at this chart. This is indeed the graph of the cubic function, x to the power of 3, x to the power 3. And as I'm saying, you extend it anywhere, it goes up, and extend it to the left, it goes down. So indeed, there's no absolute maximum, no absolute minimum at all. And for this graph, it is 1 over x squared plus 1, and clearly you can tell there is a highest point on the side at x equals 0. And no other points it is higher than this one. So indeed, this is clearly so the function has an absolute maximum at this point. And also surprisingly, even though you may see the graph, it is really getting either side, getting really close to the x-axis. But anyway, it's really not going to hit 0. So indeed, there is no absolute minimum. There's no absolute minimum here, okay. And the next graph, I hope you're familiar, or you're very familiar with this graph. This is the wave, right? The graph of waves. And also this is cosine x, right? Cosine x. So you need, if you think very carefully, and there are multiple places the function may have the absolute maximum right here or there, or more can be extended anywhere to the right, to the left. And similarly, the same function may have multiple points to hit the absolute minimum here, there, and it can be extended in either way, anywhere. Okay, multiple maximums, multiple minimums, absolute maximum, absolute minimum. This graph is very weird. But anyway, speaking of absolute maximum, I'm seeing, look at the graph, it's 2 here. No point higher than this one here. And then absolute minimum, and remember this little empty circle, which really means the empty circle, it is not a part of the graph. Which really means the function has no value at x equals 2 here. Don't take it for granted that that's negative 2. It's not. So still surprisingly, we'll say there's no absolute minimum. There is an absolute maximum, but no absolute minimum. And part E, I'm not sure if this is interesting. It might be, it should be. Because you may take it for granted that this one maximum, this is minimum. But anyway, actually, this is the absolute maximum. The absolute minimum occurs at here, right? Don't be tricked by those solid dots, okay? Sometimes they say something, sometimes they don't, okay? This is the absolute maximum, but anyway, the absolute minimum here, it is at x equals 2, at x equals 2. And also, this is the case, we do have an absolute minimum, there's no absolute maximum. And then, well, I'm seeing there's clearly a connection between those two concepts, local maximum minimums and absolute maximum and the minimums. There are connections, and we'll see the connections we will have more detailed discussion about absolute maximum minimums and the local maximum and minimums later on. And for now, make it simple. How do we find out absolute maximums and absolute minimums? So this is in general the strategy you want to consider. There are 3 steps. Okay. In order to consider the absolute maximum or minimum, first of all, you evaluate the function at the endpoints on the interval endpoints of A and B. There are 2 values. And secondly, you want to find out all the critical points. Remember, the critical points are the points where the derivatives are zeros or not defined. These are the possible candidates really for local maximums and the local minimums, right? And then you have a lot of at least 2 values from number 1, and you should have some value from step 2. Step 2, or maybe if you don't have critical points, then you don't have any value from step 2. But anyway, usually you will have some 1 or 2 or even more. And then what you need to consider here is to consider absolute extrema. Okay, absolute maximum, absolute minimum. You choose out all the values from step 1 and step 2, the largest one, that's the absolute maximum. And accordingly, the smallest one will have to be the absolute minimum. Absolute minimum. Okay. This section, it is about absolute maximum and absolute minimum. These are the steps you want to follow. Step 1, step 2, step 3. How about let's work on 2 examples from the textbook. Actually, they form a single example. They are part A and part B there. Okay. So part A, we are having a function. It's a quadratic function over an interval from 1 to 3. And so what I did here is I tried to list out those steps. Step 1, step 2, step 3, hopefully easy to follow. Step 1, I calculated the function values at the endpoints. I got a 0 and a -2. Step 2, I tried to find out critical points. They are from derivatives. In this case, I hope it's easier to see there's only one critical point. A critical point, usually it is found by setting derivative equal to 0. So clearly, setting derivative equal to 0, I got x equals 3 over 2, 3 halves. So I have a function value. From step 1 and step 2, I got 3 values. Clearly, I say 1/4. It is the largest one, right? So I say the absolute maximum is 1/4. And the 1/4, it is over 10. It appears at the point x equals 3 over 2. And the -2, it is the smallest, which is the absolute minimum. And it occurs at x equals 3. F of -3, that's -2. Low absolute maximums, absolute minimums. Part B, the function might be a little more complicated, but anyway, it should be done in a similar way. So still there's step 1, step 2. Step 1, I calculate the function values at the endpoints. And also, usually, as I said many times in my class, I just require exact answers. But anyway, this time we want to take out the largest value and the smallest value. Might be harder to figure out what this value is. So I showed the calculation. It's about -0.7. Okay. And step 2, it is about the critical points. It is found from setting derivative equals 0. And in this case, there are 2 critical points, and 1 and a -1. So, but consider what is given. Okay, for the part B, we only consider function over the interval 0 and 2. So I really should correct myself. There's only one critical point, x equals 1. -1 will not be counted, okay, because it's not in the domain. And anyway, f of 1, it is 2, well, it is 2 f, it's right here. Okay, 1 is the critical point, 1 minus 3, 1 minus 3, which is -2. 1 squared, 1 to the 3 halves, 1 to the 2/3, they are just 1, so it's just 1 minus 3. So it is the critical value f of 1, it is just negative 2. We got 3 values, negative 2, negative 0.762, 0. So clearly 0 turns out to be the largest one. So the absolute maxima is 0 at x equals 0. And then the absolute minima, the minimum it is negative 2 at x equals 1, at x equals 1. So these are the steps you want to follow to find out the absolute maximums and absolute minimums. Find absolute extrema over a closed interval. This part, it is for section 4.3, maxima and minima. Thank you for watching. I'll see you next time.